This lesson is on Charles's law. So before we get to that, we're just going to review what we did before with doing our two different types of graphs. So when we have two variables that divide to equal a constant, then we get a straight line graph. And when our x is small, our y is small. And as x gets larger, y gets larger. When we have two variables that multiply to give a constant, then we have an inverse relationship between the variables. When our x is small, y is large, and the larger x gets, the smaller y gets. And we saw in our last video that Boyle's law, P1V1 equals P2V2, is where we have pressure varying inversely with volume, and we get a curve. When pressure is high, volume is low, and vice versa. All right, so now we're going to take a look at what Charles's law says. And Charles's law, as you can see here, came out in 1787, 125 years after Boyle's law. So it took scientists over 100 years to get to the next gas law. Charles's law says, for a fixed amount of gas at constant pressure, the volume varies directly with the Kelvin temperature. This was the piece that made it so hard to come up with this law. It's the Kelvin temperature. So let's look and see that our four factors to describe the state of a gas are included in this law. So a fixed amount of gas, the amount of gas, that's our moles N. We're at constant pressure, P, and the volume, V, varies directly with the Kelvin temperature, T. PV, N, and T in our law. Okay, so it says volume varies directly, so that means that V over T, we divide our variables to give us a constant K, and that temperature must be in Kelvin. Okay, so then if we have gas under one set of conditions, so V1 over T1 will equal a constant K. If we change the volume or change the temperature, but we keep the same amount of gas and we keep pressure the same, then we will have V2 over T2 equaling that same constant K. So if they both equal K, then they equal each other. So we can say that V1 over T1 equals V2 over T2. This is the mathematical form of Charles's law that we use most often. All right, so let's take a look at an example to see if we can kind of see what's going on here, why we have this law. So we're going to consider a balloon, and we have our balloon inside our house, and we're going to say that the volume of our balloon, our V1, is 33 liters, and the temperature, it'll be close to room temperature, so we'll say it's at 24 degrees C. That's like a normal room temperature. And we'll go ahead and put our particles in the balloon, and we'll put in 10 so we can keep that constant because number of moles has to stay the same. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so our gas particles in the balloon, they are all moving around, they're bumping into each other, and they're hitting the sides of the balloon, pushing the balloon out. So our gas particles are all pushing the balloon out. They are exerting a pressure. Now, outside of the balloon, we have our atmosphere, our nitrogen gas, our oxygen gas, a little bit of carbon dioxide gas, and the gas molecules in the atmosphere are bumping into the balloon, and they are pressing in on the balloon. So we have a balance here. The gas inside pushing out, the gas outside pushing in. And we are at a temperature, and we've learned that temperature is a measure of the kinetic energy. So our temperature is proportional to our kinetic energy. So this is a direct relationship. As temperature goes up, kinetic energy goes up. Well, why is that important? Well, our kinetic energy equals 1/2 mass times velocity squared. So this is the mass of the particles and this is the speed, how fast they're traveling. So this means that temperature is proportional to 1/2 mv squared. So what this is telling us is that if the temperature goes up and our mass stays the same, if our particles are the same, the mass stays the same. If the temperature goes up, then the velocity also must go up. So all these particles, they're traveling, if they're all at the same temperature, they're all traveling with the same speed. Some a little faster, some a little slower. But the average speed is directly proportional to the kinetic energy to the velocity squared. Okay, so now we're going to take our balloon and we're going to bring it outside where it's really cold. So we're going to take this balloon and we're going to bring it outside. And this is going to be our interim state. Okay, so we have our 10 particles. And now we are outside on a really cold day. So we'll say our temperature equals -20 degrees C. So what does that mean in terms of how fast the particles are traveling? Because our temperature goes down, now the particles are at a lower temperature, they travel more slowly. So they start hitting the sides of the balloon less frequently. So the pressure inside the balloon goes down. The pressure outside stays the same. So that means the pressure outside is going to push our balloon and make it smaller. So that'll be our next step. Well, let's write down what happens here. Okay, so at lower temperatures, at a lower temperature, and a lower T, our gas particles move more slowly. So they hit the sides of the balloon less frequently. And the pressure inside the balloon, the pressure of the balloon goes down. Okay, so when that happens, the pressure outside of the balloon is stronger. So then the pressure outside is greater than the pressure inside of the balloon. So the atmosphere pushes in and makes the balloon smaller. Until the pressures are the same as they were before. Okay, so what happens then, now we have our balloon with our 10 particles. The temperature is less, the volume goes down. For this reason, at this point now, our particles are moving slower, but now they are equaling the pressure of the atmosphere pushing in because they have less distance to go. So this is our final. This is our V2. We're going to calculate what that is. And this is our T2 equals, what do we say, -20. I'll put a decimal point there, degrees C. So these two, the pressure in the balloon is the same. So this pressure, we'll call that P1, and P2 are the same. P1 equals P2. These guys are moving slower, but they have less distance to travel. These guys are moving faster, but they have more distance to travel, but the pressure ends up being the same. So that is what's going on. So you can actually try this. You can take a balloon, blow it up, get a string, put the string around the balloon, then you can see what length that was. Put the balloon in the freezer, let it stay in there for a good while, and then put the same string around the balloon in the freezer, and you'll see that your balloon actually gets smaller. And if we were to take this balloon outside again, it would expand outward again. All right, so let's actually figure out what our new volume is under this set of circumstances. So we use Charles's law. V1 over T1 equals V2 over T2. So he said our V1 is 33 liters and our T1 is 24, but we have to use Kelvin temperature. There's no choice here. You have to use Kelvin. So 24 and 273 gives us 4 and 3 is 7, 9. So we are at 297 Kelvin. 297 Kelvin. You can't have negative numbers, so we have to have Kelvin. Equals, we're looking for our V2 and our T2. So we have 273 and negative 20. So we get 253 Kelvin. Because if you had a negative temperature here, you would get a negative volume. We don't have that in chemistry. You can only have positive volumes. Okay, so let's do that on our calculator. So you can cross multiply, or you can just multiply each side by 253K to get rid of this, because we need to get V2 by itself. Kelvin cancels Kelvin. Our unit is liters. And let's see what we get. So 253 times 33 divided by 297 equals. So our volume is 28.1 liters. Started out at 33, the temperature went down, the volume went down. The temperature goes up, the volume will go up as long as the pressure stays the same. All right, that's it.